Lesson 1.2a, Introduction to Logs and Their Characteristics. We're going to take a look at doing log regressions and take a look also at what is similar to the log graph, the log equation, and an exponential equation and exponential graph. So if we take a look here, we know we can solve exponential equations algebraically or graphically already. We can solve it by putting one equation on the left into y1, the other equation on the right into y2, and then we look and see if they intersect. When they intersect, that is our solution. So we take the x number from our intersection, and that solves for x in our equation. Now, this lesson, we're going to learn how to solve some of these algebraically. Now, if you take a look first, let's look at the example on the bottom left. Everybody take a few moments and put equation, the one on the left, into y1, 2 exponents x plus 1. But don't forget, because you have exponents, with more than one thing, it needs to go in brackets. Then on the right-hand side, scroll down to y2, and you're going to put in base 5 exponents, x minus 1, again in brackets. Okay, I'll give you a couple minutes to do that. Push play when you're ready. Okay, taking a look at those, you would have found your intersection point 2 decimal places. We would have found this intersection point here being 2.51 and 11.42. Now, just the coordinate point 6, we have x on the y, so our solution is 2.5, because we're looking for the x value. You guys try the one on the right here. Let's do this one again. Push pause, and then when you're ready, push play. Okay, well done, everybody. Let's take a look. The one on the left went into y1. The one on the right went into y2. Let's see how far you guys got. So, this one you're going to need to take your window. The window on this one is going to have a y max of 100. Otherwise, you're not going to be able to see where they intersect. So, the intersection that you would find is 8.89 at 71.39, rounding to 2 decimal places. So again, our solution is the x value. Moving on. So when we have different bases, we need to use logarithms to solve different bases. So first of all, in order to use logarithms, we need to know how to convert exponential equations into log equations, or log expressions. So then we need to know what the heck is a log. Well, just like every operation in math has an opposite or inverse function, so do exponents. Logs are the inverse or opposite function to exponents. So the word logarithm just means power or exponent. So let's take a look at how they're related. First, because they're inverse functions, algebraically you must switch the x and the y values where they stand in the equation. But that leaves you with y as an exponent. And at this point, we don't know how to solve for y as exponents because the equation now is going to start with x equals. And our calculators don't know how to put x equal equations into our calculators. It just doesn't belong there. We have everything saying y equals in our calculator. So in order to solve for y, we need to be able to undo exponential equations to get the y out of the exponent position. That's what we're actually trying to do. So in order to do that, we need to find how to change the exponential equation into a log equation. So here's how they're related. Let's take a look. Converting from exponential to log form. So we know that our first exponential equations we take a look at, if we just have a b value, we do have an a value. It just hides. It's a hiding 1 for an a value. So the y-intercept there is going to be a 1 because we know that the a value is the y-intercept. Okay, then we take a look. If we want to do inverse, so we're switching things to inverse, that means the x and the y switch places in the equation, and it becomes what we see on the right-hand place, on the right-hand side. And we do the exact same thing if there's an a value. If there's an a value on the left, it just sits exactly right beside the b value on the right. Now, since we have it now converted as an x equals equation in either order, we need to be able to convert it to log form. So this is what they're saying that the left-hand equation is equal to. They're saying take the y out of the exponent form, and then you need to put the base of the variable y on the left as the base of the log. So the base is the same. But now the exponent and the variable x, they switch positions, and now you actually have the exponent coming out, or the y coming out of the exponent form. But he's now on the same level as your x, which means you can now solve for y. Same thing happens, only now with a times b to the y, only now we have the a sitting in front of the log word. So it says when converting the inverse of exponential equations to log equations, the y is converted from an exponent in the exponential equation to the actual answer of our log, which can now be graphed. Y equals in our calculator, as long as we have a base 10 or base e. So what the heck does that all mean? Let's investigate further. Let's see what a log looks like. So this is what our log equation looks like, just like we had the one that looks like our logs on the top right-hand side. So what that actually means and how we would read it is, what power of 10, so I don't know the power of 10 would equal or is 100. So, can we work it out in our head? What power of 10 is 100? So 10 to the x is 100. Well, hopefully we all know that 10 squared is 100. So in this case, x equals 2. Let's see why that's related and why it goes together like that. So let's read these exponential equations. So when we read the top one, we would say, what power of, which is our red x, of 2, which is our base 2, is 32. So that's exactly how we're going to read that. What power of, and I've color coordinated it here where the what power of part is red, which matches our x exponent as red. Our base number is blue, and so is our 2 as we read the equation. And the is also black as the equal sign, and 32 is also purple matching. So it's just showing you which parts of the equation match to how we read that equation. Let's see how we read the log equation. Is it similar? Absolutely it is. So this time now we have the arrows are pointing to which parts match. What power of 2, there we go. The red here means what power of, and the x belongs with that as well, 2 is 32 is the way we read that. Now, I know it's a little bit confusing right now. Let's check and see how it would work out when we actually relate them together. So, here's how it all relates together. So it means that if you've got the y, he's got the value of the logarithm. But in our exponent form, he's actually our exponent. Now, in the equation here, our base of our log is still b. Well, the base of the equation for an exponential is also b. Now, it says inside the log, the x is called the argument of the log. The argument of the log is actually the answer of the exponential. And there's another hint here. The arguments can never be a negative number. Okay, so the argument can never be a negative number. So that's the number or the value sitting right beside the log word. Not the one that's dropped down like the letter b, but the one like the x. So we take a look at the bottom here. What do we notice about these two equations when we compare them back and forth? Well, right now I've got a base 5, and we call it our base of our log if it's written subscript lower right beside our g. Our exponent 3 becomes the answer of our log, and then we've got our answer of our exponential becomes the argument of our log. Okay, so answer and argument, they match. Let's take a look at some actual equations here. So in log form, this is how we would set them up. This is how it relates. On the left-hand side, we have what power 2 is 8. We get the 3, the answer of our log. Well, as an exponential form, we have 2 exponent 3. So the 2 to the power of 3 gives us 8. Now, 8 again, we see is the argument of our log. They mean the exact same thing. Let's do a couple examples and convert these. So if I'm going to convert these, the biggest thing I have to remember is my base is going to stay the same. So I'm going to highlight my base. My base on this one is a 4. On the right-hand side, example 2, my base is a 3. How do I know those are my bases? Because they're the ones with the exponents. Same thing, example 3, the base would be a 2. And on example 4, the base is also a 2. It won't be the 10. So let's take a look at how we would do example 1. So I'm going to write the word log first. That's always the way I start. I write the word log. My little base number, that highlighted 4 that I've chosen, I write it right beside our G as a subscript. It goes lower. Then I want the answer of my exponential. He's going to sit right next to my log word, which is n, and that's going to all equal our exponent x. So now the exponent moves down into the answer of our log. Let's try example 2. Just because we've got more than one thing on the left-hand side, it doesn't matter. We just need to put it in brackets because there's more than one value. So again, I start by writing the word log, my little base number in front of log, which is, or on the base of the exponent, is a 3, so it's going to be my subscript 3. The answer here is going to be my p minus 2. Again, it's in brackets. And that's going to all equal my exponent, 5 minus x. So the exponent comes down as the answer to the log again. All right, you try examples 3 and 4. Example 4 can be a bit tricky, so if you get stuck on that one, just wait for me and I'll help you out. All right, push pause now and push play when you're ready to move on. Okay, you got a couple minutes to look at that. Let's see how we go. So again, I'm going to start by writing my word log. I'm going to put the base 2. I need to put the answer of my log as a fraction, but again, because it's a fraction, it needs to go in brackets. So it's going to be 16 over 5, all equaling my exponent of negative 4x. Check your work and make sure that's exactly what you got. Example 4, we've got an a value. Now, the a value needs to be divided out to both sides. How come? Because we don't want it sitting beside our base. So we're going to divide the 10 out. That's all we know how to do yet before we know log laws. So then that's going to give me 2 to the t over 7 equals y over 10. So now I can actually convert that to log form. So what that's going to look like, again, I start with writing my word log first. My base of my exponent is my 2, so it's the base of my log. The argument or answer is going to be my answer of my exponential. So I'm going to have y over 10 in brackets beside the word log. And that's going to all equal the exponent I started with on the right hand, on the base of the 2, which is going to give me t over 7. Okay, check your work and see how you did. Okay, there's a couple more examples. Let's try these ones. Now we're going to work backwards. We're going to go from log form to exponential. This form is actually a lot easier to work with. So let's take a look. How are we going to write a? Well, we need to start with our base. So I take a look at the base of my log. That's going to be the base of my exponent. So it's going to be the base there, number 7. The answer is going to be my 4. He is my exponent. And that's going to be all equal to my x, the argument of my log. Check your work and make sure that's what you get. All right, let's try b on the right-hand side. We're going to do the exact same thing. So my base is base b of my log, so it's going to be base b. Then I've got my exponent, which is the answer of my log, which is an m. Then I have that all equaling to capital T, which is the argument of my log. Try C and D, push pause now, push play when you're ready. Okay, we got a couple minutes to look at that. This guy has a base x. The exponent on the base x is going to be root d. And that's going to all equal 4p squared. Excellent. Let's move on to the right-hand side. Now, if you notice in letter D, there's no base written. If there's no base written, it's always a hiding 10. So, the first thing I need to be able to do first, though, is I need to be able to divide that 4 out. So I'm going to divide the 4 out first. But before I can divide my 4 out, I must take a look and see. I've got a subtract D on the right-hand side. Whenever there's a plus or a minus, not something attached to the front of the log, but something at the end, we need to get rid of that, because it's not in brackets. If it was in brackets, it would belong together, but it's not in brackets. So I need to move this t over to the left-hand side. So what I'm going to do is I'm going to add t to remove it. So I'm going to add t to both sides. Then I rewrite my equation. I get 5x plus t equals 4 log 3 cubed. Now I need to get rid of that 4 by dividing it out. Just like algebra steps. Same process. Now I write the left-hand side. I've got 5x plus t over 4 equaling log of 3q. Now remember, that's a hiding 10 on log if we don't know that already. So let's set that up as an exponential now. Since I know it's a base 10, my 10 is my base. And then my exponent is now the left-hand side of the equation in brackets because there's more than one thing. 5x plus t over 4, all equaling the 3q. Okay, a few more steps, but we get the exact same answer doing the same process. Let's move on and see what this next challenger question looks like. Give it a try. Push pause now. Push play when you're ready. Okay, we'll take a look at this one. It's giving you a value, so we're going to convert the first one to exponential. If I convert the first one to exponential, I get 2 exponent 3 equals my x. So I can solve for x and then input that value into the x in their second equation. So 2 exponent 3, I know is going to give me an 8. So x is 8. So now I'm going to put the 8 into the other equation. So it actually looks like log base 2 of t equals 8. Now I'm going to change that one to exponential. I'm going to get 2 exponent 8 equals my t. So now I can solve for t. In my calculator, I type in 2 exponent 8. And what am I going to get? 256. So t is equal to 256. Okay, moving on. What about base e? Well, we've got a base e, and it's called Euler's number. Can it also be converted to log form from exponential? Absolutely it can. Yes, it sure can. But it's written differently, and it's got a different button on our calculator. But remember, like pi, Euler's number letter E is the symbol for irrational number. So when we actually put it in our calculator, it's going to show up like E with a little box there. What that little box means is you need to put an exponent on that base E. So the exponent you should put on there is a 1 unless they have something else written. So everybody in their calculator, please type in E exponent 1, enter, and see what you get for an answer. When you do that, you're going to get 2.718, and it's a run-on decimal. So if I've got this equation, y equals e to the x, that's an exponential equation. Well, can I convert that to a log equation? Yes, I can. Let's see how we're going to do that. Okay, so yes, it can, and we're going to see our details now. So if we want to write, again, we're going to put log, and this one is going to be a base e. How come log base e? Because that's what we were told. Now, it says y equals e to the x. So y equals e to the x. We need to change our x and our y to get it into our form that is what we call the inverse form. So I have my inverse form here now. So I switched my x and y around. So now if I write that as a log, it becomes what you see on the left here. I still have my same base e. I have my x as my argument. And then I have my y as the answer of my log, whereas it started as the exponent on the right-hand side. So now I'm going to just convert my left-hand side here. Now, why do I have to convert it? It's because it's a base e. The word log uses base 10. But a different button on our calculator called log, it is a base e. Okay, so this is what we use for base e. So I would not write a log as log e x. I would write it as log e gets replaced by the word log. Okay, so log, when you write it down, has an invisible base e there. Just like when you write the word log down, I wrote log x. Log has an invisible base 10. So log is base 10 and log is base e. Do we have to write their bases? No, we don't. They are always assumed to be what we know as the two inverses. Okay, let's take a look at the next section. Now we're going to take a look at how the graphs are compare up. So we've got an exponential graph and a logarithmic graph. How do they compare? What do log graphs even look like? Well, we're going to see here how a log graph looks. The log graph only uses the right-hand side of our Cartesian plane. So we're using the up and down part of y, so we're using the whole y-axis, but we're only using the right-hand side of our x-axis. So we're going to see that it goes from quadrant 1 and quadrant 4. So quadrant 1 is our positive. So if we have this guy here, we always read a graph from left to right. Where does this graph start? For left-hand side, it starts left at the bottom and then goes up. So since this one goes up, we call this an increasing graph. It's an increasing graph. Okay, so an increasing graph is always going to go from quadrant 4 to 1. So that's an increase. Then we take a look at the right-hand side. On the right-hand side, my graph now is going down from left to right. So that means that that's a decrease. This is a decrease. Okay, this is a decrease. Now, if in a decrease, it's going to go from quadrants 1 to 4. So that's a decrease. So it's starting in the positives and going down to the negative part. Now, how does the domain and range differ from an exponential? Well, let's take a look. On our log graphs here, we have a domain boundary, whereas on an exponential graph, we did not have a domain boundary. We had, on an exponential graph, we had exponentials rising to the right or falling to the right. So they were always going from quadrant 2 to quadrant 1. So they use the top half of the Cartesian plane, the full x-axis and only the top half of the y-axis. However, our domain there, on this one for exponentials, we had a y boundary because we didn't go to the bottom half of the y graph. So on exactly opposite is a log graph. We do not see the left-hand side of our x's. They don't exist for a log. So that way, our domain actually has a boundary. And now it's not going to touch our y-axis as well, so which means it must be greater than 0. Because we considered our y-axis our horizontal asymptote. Okay, it's a horizontal asymptote. And what does that actually mean? That's a line the graph approaches but never ever touches. So it's going to come very, very close to the y-axis, but it'll never touch. So it'll never have a y-intercept. So the number of y-intercepts, 0 because there are none. It'll never have a y-intercept. It doesn't intersect the y-axis. It will have an x-intercept, absolutely. And for all case and purposes, the ones we deal with, the x-intercept is always 1 and 0. Now, the range, if we take a look at range again now, range is our up and down boundary. We're not going to have a boundary on our y because we're in the top half of the quadrant and the bottom half of the quadrant, which means I use all the positive y numbers and I use the negative y numbers. So that means I've got no boundaries on my range. Okay? Only boundaries on the x because I never touch 0. I have to stay right of 0 for my graph. Okay, so let's now compare those. If I have an equation then, the log equation is going to look like this, or it's going to look like this. And the a value is what tells us up or down. In an exponential, we have y equals a times b to the x. And here it was the b value that said up or down. That is not what happens in a log graph. The b value does not tell us up or down. It tells us, the a value tells us up or down. So this a value is very important. So that's why it's giving us a boundary on our graph that we can see right up here. It's showing you that a is greater than 0. If a is greater than 0, then it must be going up. Okay, it's increasing because it's larger than 0. On the left-hand side, I've got a is less than 0, and that means my graph is going down away from the y-axis. Okay, so let's take a look. How do we actually write these out? Well, when we convert the two forms, we know where the b sat, but where does our a go? We're going to notice for exponentials, the a goes at the front or inside b. In a logarithmic, the a goes in front of the word log. Now, when we actually use our log regressions, it actually is going to show up a little bit differently because log regression, we actually use the ln button. So it's going to look a little bit differently with a ln. So we could actually write it this way for ln. So we have, or we would have a plus b times by ln of x. Now in this case, it's going to be the b value attached to the word ln, just like it's the a value attached to the word log. So it's the a value in log. It goes in front of log to tell us up or down. On the right-hand side, on the left-hand side for exponentials, the b tells us up or down. A is still hiding in front of the b. But in a ln graph or a ln equation, we notice that the b must also sit beside the word ln, and the b is going to tell us up or down. So let's take a look at a couple examples. If we graph all of these on the same grid, put them into your y equals, please. Put the first one into y1, the second into y2, the third into y3, and the fourth into y4. Let's take a look and see what those graphs look like. Push play when you're ready. Okay, so what you should have noticed is the very first graph is our basic graph. It's just going to increase and go up through positive 1. Now on the second one, I have a number in front of log that's larger. So that means it's going to go up even farther than the 1. Than the one we just drew. Because how come we have a hidden 1 in front of our log on the example 1? Example 2, we have the number 2 in front, which means it's further away from the x-axis. On the right-hand side, or on the third example here, I've got a -2. That -2 means it's going to go away from, going down below, and again, it's going to be further away from our x-axis. The one that says -0.5, -0.5 is going to be lower, but again, it's also going to be going closer, though, to the x-axis. Okay, so the smaller the number gets, the smaller numbers are closer to the x-axis, the larger numbers are farther away from the x-axis. So let's take a look. We had graph 1, whoopsie, we had graph 1, then we had graph 2, we had graph 3, and we have graph 4. Okay, moving on. This is what our general log graph looks like if I just have log base 3 of x. So if I want to answer my questions here, it's saying, how does the a value alter the graph? The a value alters the graph by, as we just acknowledged, how far away from the x-axis it is. So the a tells us how far away the graph is from the x-axis. Okay, write that down, push play when you're ready. So now we're going to pull up the rest of them. Domain. As I said, I need to be on the positive x's only. So that means I can never touch this y line. That is my vertical asymptote. That's the x equals 0 line. So that means my domain has to stay to the right-hand side of that. I can never be touching it. So that means my domain, my x, does have a boundary. So I'm going to say that x must be greater than 0, but after that it can be any number possible. So it could be a fraction or a decimal or a square root or a non-perfect square root. It could be absolutely any digit as long as it's greater than 0. So then we say XCR after. The range, as we see it, goes up and down in our y quadrant. So it goes up into the positive y's, down into the negative y's. So the range has no boundary. So we say no boundary. And how do we write no boundary? We say y, e, r. That's our range. The x-intercept, the one that we only ever worry about, yes, there is one, and it's always at 1, 0. Here's our x-intercept. The y-intercept, there never is any, so we say none. We never say 0 because that would mean it actually touches our 0. It doesn't touch 0. We just don't have one. And the asymptote. Again, the asymptote is the line it comes close to but never touches, and that would be our x equals 0 line. So the asymptote is going to be our y-axis, okay, where x equals 0. Now, are there any differences between log functions between 0 and 1? Well, all it shows us between 0 and 1, again, that we investigated, was it shows us how close to the x-axis that we're going to become. That's all that's actually showing us. Let's try a couple examples and put them into our calculator and draw the graphs. Okay, example 1, put that into y1 in your calculator, and let's draw the graph and analyze its characteristics. You're going to notice that almost all of them are the same, except for increasing, decreasing, and end behavior. Those are the two that are going to be different. Everything else should be standard for a log graph. Give it a try, push pause now, and play when you're ready. Okay, we put this guy into our calculator. We're going to notice that it's going to come down, and it's going to start, it's a positive, so it's going to go up, and it's going to cross through positive 1 always, and it's going to go up away. So it is an increasing function, and the end behavior goes from quadrant 4 to 1. So I'm going to say quadrant 4 to quadrant 1. Okay, everything else is standard. X-intercept is always at 1, 0. Y-intercept, we don't have any, so there's none. Domain, there's an X boundary, it must be greater than 0, and then any real number. Range, there's no boundaries, so it's Y-ER. And the equation of our horizontal asymptote, that's our vertical y-axis where the graph never touches. So we're going to say that's called x equals 0, or you could also call it the y-axis. Okay? Let's move on to the next example. Put those two into your calculators and do the exact same thing. Okay, on this one we would have noticed we would have had an increasing and decreasing function. So if I actually take example 2 and 3, and I do it this way, put example 2 here, example 3 here. Example 2 is going to be a decreased graph because it's got a negative, and then we're going to notice that example 3 is going to be an increased graph because it's got a positive. Okay, so let's draw both those graphs. They're both going to cross through positive 1. So sketching the negative graph, it's going to be further away from 0, meaning the x-axis, and in the positive one, it's going to be closer to 0. Okay, so it's going to be closer. So something similar to that. X-intercepts, always at 1, 0, and it's a coordinate point, put it in brackets. Y-intercept, we never have any, so we would say none. And then domain again, x boundary, x greater than 0, and then it can be any real number. This will be the same. Range, Y-ER, again it's the same. End behavior is different. So for graph 2, I was going from quadrant 1 to quadrant 4 because it's decreasing. And the next one I'm going from quadrant 4 to quadrant 1 because it's increasing. The equation of our horizontal asymptote is always the same. It will be x equals 0. Okay, which is our y-axis. How are we going to decide our characteristics here? What we want to do is we just want to compare them. Again, they're going to be inverse functions, so we're going to notice that these should be opposites in every way. Fill this chart out, do what you know, push play when you're ready. Okay, about a couple minutes to look at that. So our domain we know for an exponential. Domain can be any real number. We don't have any boundaries. Same thing as we have on a range. No boundaries on our range for our log. So those get our XER and YER. But the ones that have boundaries, for exponentials, they have a boundary on the range because they do not go below 0. So we would say y must be larger than 0, and then it can be any real number. On our logs, the x has a boundary because we never go left of the x as 0. So that must mean that x must be greater than 0, and then it can be any real number. The x-intercept is always 1, 0 for both of them, the ones that we're going to worry about. And the y-intercept, again, is standard for both. There's none. Oh, pardon me. Oh, let's get that right again. Okay, x-intercept, we're going to have none for exponential. No y-intercept for a log. It's always 1, 0 for a log, and the y-intercept is always the a value in an exponential. Equation of the asymptote, again, these are opposites. So exponentially, we are going to have a x-axis, which is going to be our y equals 0 line. And then when we've got our log graph, it's going to be the y-axis, and that's going to be our x equals 0 line. Okay, so you're going to notice that these two functions are completely opposite. Okay, another word for opposite we use is inverse. So So what you're going to do right now is you're going to take a look and you're going to investigate the inverse function. And you're going to take and use the numbers in the charts as the exponents on x in the first equation and the exponent as y in the second equation. So when you've got those filled out, push play when you're ready to move on. Okay, you're going to notice that the first one, our graph of y equals 2 to the x, that's going to give us 1/8. We put our exponent as -3, then 1/4, then 1/2, then a 1, 2, 4, 8, 16. You're going to notice the exact same numbers on the x. 1/8, 1/4, 1/2, 1, 2, 4, 8, 16. Let's graph those. So, the exponential one I'm going to have, and I'm going to graph this one. So we're going to have this guy coming up. And then we're going to be down there. And it's going to come up here. There's our exponential graph. We're going to join our points. Now we're going to do our exponential graph of the inverse function. So our 2 to the y. So that one's going to be exactly opposite. So we're going to have this guy down here coming down here. Okay, so we're going to notice this is going to come up like that. Now, what line did you notice that they actually reflect on? Well, if we draw a diagonal line, it's called our y equals x line, that would be considered our reflection line. So these guys are exactly reflected from each other. Okay, they reflect off that, which means they're going to be inverse functions. So x1 is my x equals 2 to the y. And the blue one on the top here is my y equals 2 to the x. Let's take a look again at the characteristics. So, domain of our exponential is going to be XCR. Range of our exponential is going to be y greater than 0. YER, x-intercept, none. Y-intercept is going to be a value. Asymptote is going to be the x-axis, which is y equals 0. Let's do the exact same thing for our log graph. We're going to have x is greater than 0, XER. Then we have YER, no boundaries on our y. X-intercept always at 1, 0 that we know. There's no y-intercept that we deal with, and it's our y-axis, which is our x equals 0 line. Okay, let's take a look at what those graphs look like if it's a long graph, because these are base 2, so that's actually very similar to what we would do for a log base 10. But now how would it look if it was ln and base e? They're going to look identical, absolutely identical. So base e has an inverse, and base e's inverse is known as our ln button. Alright, the next section is the practice section. Do the practice section and see how you do. Check your answers. This concludes lesson 1.2a.